Okay, in this next section, we're going to talk about phase changes. And remember, phase is just another word for the physical state of matter. And we all know that there are three physical states or phases, and we're very familiar with those: solids, liquids, and gases. Solids, liquids, and gases. At least the basic phases that we're dealing with. We're not going to be dealing with the aqueous state indicator or plasmas or any other of those sorts of physical states that have been discovered, but really just focus on the three basic physical states. Now, when a substance transitions, converts between two phases, but does not change its chemical composition, it undergoes a phase change. And remember that a phase change is just a physical change. It's not a chemical change. Because again, we're not changing chemical composition. We're just changing its physical state, so this is a physical change. Just a little note there to remind us that we're not changing the chemical composition. So we can have a triangle diagram that will allow us to consider the phase transitions and the names for each type of transition. So I'm going to put gas up here, then I'll put liquid, and then I'll put a solid. And generally, as we increase the temperature on a substance, we convert from solid to liquid to gas. But this can depend on the pressure as well. And we'll talk more about that when we discuss phase diagrams. But for now, we've got these three physical states, and we can convert from one physical state to the other, and that's what that arrow signifies, or from that physical state back to the other one. And we can have these conversions between any two of these physical states. So I can convert from a liquid to a gas to a liquid to a solid. And this is one that you may not be that familiar with, and that's converting directly from a solid to a gas without going through the liquid first. So these are all physical state transitions, and this is called a triangle diagram. So each of these processes has a name, and I'm going to use a different ink color for the name. So when we go from a solid state to a liquid state, generally we call that melting. Right? And when we go from a liquid back down to a solid, we call that freezing. Okay? So we could melt from a solid to a liquid, or freeze from a liquid to a solid. When we're converting between liquids and gases, if we go from liquid to a gas, we call that vaporization, because we are converting a liquid to a vapor. And there are a couple of other terms that we use for this. We also call this boiling or evaporation. So they all refer to the same process, converting from a liquid phase to a gaseous phase. Now, in common use, the terms boiling and evaporation, they mean the same thing, but we use them in two different contexts. Usually, if we are intentionally putting heat into the liquid to get it to vaporize, we call it a boiling process. For example, if you're boiling water on the stove. In contrast, if we are just allowing a liquid to vaporize on its own, and it absorbs ambient heat energy from the atmosphere around it as a passive process, we tend to call that evaporation. But they all mean the same thing: vaporization, boiling, and evaporation. We're converting from the liquid physical state to the gaseous physical state. Going back the other direction, going from a gas to a liquid, this is condensing. Condensing. So for example, if you have a very cold drink in a glass and it starts to form moisture on the outside of the glass, that is the water vapor in the atmosphere, the gas in the atmosphere, that is condensing into a liquid. Okay, that leads us to this last set of conversions, from a solid directly to a gas or a gas directly to a solid. And I don't have a whole lot of space here, so I'm just going to say this process where I'm going from a solid to a gas without going through the liquid first is called sublimation, S-U-B-L-I-M-A-T-I-O-N. Something sublimes. It goes through sublimation. And a classic example of this is the substance called dry ice, which is solid carbon dioxide. And when it starts to heat up, rather than melting into a liquid, it forms the vapor, the gaseous carbon dioxide. When we go the opposite direction, and we go from a gas directly to a solid, we say that we are depositing solids from the vapor phase. So this is deposition, because we are depositing solid particles directly from the vapor. So we have vaporization and condensing, or condensation, I guess, freezing and melting, sublimation and deposition. Okay? That's just a little triangle diagram so that we can talk about these phase changes. All right. In this next section, let's fill in some gaps here. When a substance undergoes a state change, which is what we were talking about above, the temperature of the substance does not change or stays constant. The temperature of the substance stays constant while or during the transition, while the transition is taking place, during the phase change. However, while the transition is taking place, heat is being absorbed or given off. So the temperature is not going to change while we're undergoing one of these phase changes, but it is still, the substance is still going to absorb or give off heat. If the chemical substance is absorbing heat, we know that that's called an endothermic process, because it is taking heat into the substance. In contrast, if heat is being given off from a substance during a phase change, we know that's an exothermic process. So we can draw a little graph of this process, and it's called a heating curve. So I'll make a large y-axis and a large enough x-axis so I can write in here. Over here, I'm going to say this is the temperature on the y-axis. And over on the x-axis, this is going to be the heat energy. And let's start out with a 0 temperature. We'll call this 0 Celsius, 0 degrees Celsius right there. And we'll also make 100 degrees Celsius right above there. Okay. So we have a temperature scale here. It's in Celsius. And this temperature scale, there's the 0 degrees Celsius, there's the 100 degrees Celsius. And this is for water. We're going to assume that this is at 1 atmosphere of pressure. So let's imagine we take an ice cube out of our freezer. And the ice cube is at some temperature below 0 degrees Celsius, below freezing. So it's in a solid state there. And then I'm going to put it in a pan, and I'm going to put the pan on the stove, and as I start to add heat energy, increasing heat energy, the temperature of this substance is going to increase. So I'm going to plot the temperature increase as I add heat energy. So I add a little bit of heat energy and the temperature increases. Add a little bit more and the temperature increases. So you get the idea? And then I get to the phase change temperature. In this case, it would be the melting point of the water. And now, as I am adding heat energy, as we set up here, heat is being absorbed by the substance, but the temperature is going to remain constant while the transition is taking place. So again, I'm continuing to add heat, the temperature increases, and then once it gets to the phase change temperature, the melting point, the temperature stays the same. And the temperature is going to remain constant, staying the same until all of that solid water is converted into liquid water. So I'll represent the liquid water there with little waves in it. And now I continue to add heat energy. And now the temperature is going to start to increase. Because I've got liquid water and I'm increasing the temperature of the liquid water. I get up here to the phase change temperature, the boiling point of the liquid water, and I'm continuing to add heat energy, and you know what's going to happen? The temperature is going to level off for as long as it takes to convert all of that liquid water into vapor. So I'm just going to make some vapor there. These are not, I should do that in a different color, shouldn't I? Just so that it's not mistaken for plots on my graph. There we've got a vapor now. And so now the liquid water is converting to steam. Now if you had an open pan on the stove, then all of the steam would just boil away, right? But let's say you had an enclosed container so that the steam couldn't go anywhere. Well, now additional heat energy is going to go into increasing the temperature of that vapor. And what happens? The temperature of the vapor would increase. So here again, when a substance is undergoing a state change, changing its physical state, the temperature of the substance stays constant. That's what we're seeing in these flat regions while the transition is taking place. However, even though the temperature is remaining stable, we are still absorbing or giving off heat into the substance. In this case, we are absorbing heat into the water sample. Well, why does this happen? Well, that's what this is talking about down here. Basically, we have solid water particles. And the solid water particles, the water molecules, have a certain amount of kinetic energy in each of the molecule. That's what we call heat energy, right? By heating it up on the stove, we are increasing the average kinetic energy of that sample. And you recall that temperature is related to the average kinetic energy in the sample. So we're increasing that average kinetic energy in that ice cube until we get to the point that there is so much kinetic energy in those water molecules that they start to vibrate so much that they start to break apart the intermolecular forces that are holding them together. And then we start to break apart some of the IMFs. We break apart some more of the IMFs. We break apart some more of the IMFs. And as long as we're doing that, the heat energy that we're putting into this is not increasing the overall average of the kinetic energy. It's just breaking those IMFs. So that's what the heat energy is being used for, is to break the IMFs. Once all of the IMFs in that solid are broken and we have a liquid, now the molecules can flow past each other a little bit, but there's still a little bit of attraction, intermolecular force attraction between them. But now as I add heat energy, I'm increasing, again, the statistical average of the kinetic energy in that liquid sample. Again, we get to the phase change temperature, and now I'm going to be breaking intermolecular forces again. So I'm breaking the intermolecular forces holding the liquid molecules to each other. I break some more, break some more. And the heat that's going into this sample is breaking those IMFs. Until finally, all of the IMFs from the liquid are broken, which means each of the molecules goes off alone by itself. And that's a gas, that's a vapor. If it were in an open pan, as I say, this gas would just go off into the room and then start cooling down. But if it's in an enclosed container, then the heat energy I could add to it would again go into increasing the average kinetic energy of those gaseous particles. You can see what's eventually going to happen if this is an enclosed container. As this gas increases its temperature, well, we know that volume and temperature of a gas are directly proportional, and so this gas is going to increase in volume, it's going to increase its pressure inside the enclosed container, and depending on the container that it's in, it could eventually explode the container. So let's fill in some gaps down here. Notice that solid ice increases in temperature as heat energy is added until it reaches its melting point right there. At that point, heat continues to be absorbed, but the temperature does not increase. Instead, the heat energy is being used to break intermolecular forces to achieve a phase change from solid to liquid. And this energy required to break the intermolecular forces to melt a solid, again, the energy required to break the IMFs, in that solid, the energy required right here to break all those IMFs from the solid to form it into a liquid, to melt it, is known as the substance's heat of fusion. Heat could also be called enthalpy. Okay, so the substance's heat of fusion is basically right there. That's the heat of fusion, the amount of heat energy required to do that. Or we could abbreviate it, the change in enthalpy, the change in heat, the change in enthalpy, for the process of this. Now we call it the heat of fusion. Even though we're not fusing the particles, we're actually breaking them apart. But you can see that the enthalpy required to go in this direction, from solid to liquid, is exactly the same amount of energy that would be given off if we were to go back the opposite direction. So the amount of delta H change is going to be the same whether we're melting something or freezing it. And so this is called the delta H sub F, the change in enthalpy, fusion, or the melting. They're opposite processes, so it's going to be the same delta H with just different signs. And we'll do a problem here in a moment to show how that works. So, delta H sub F, okay? Moving on. Now here's an opportunity to actually do some calculation using the delta H of fusion. I'm giving you the value of the delta H of fusion. It requires this much energy, that many joules per 1 mole of water to get it to melt. That's the amount of energy that you have to put into water, solid water, to get it to melt per mole. And if we were going back in the opposite direction, if we were freezing the water, if we were fusing it, then it would be the negative sign, and that would mean that that's how much heat energy would be required to be released from the water, from the liquid water, in order for it to become solid per mole. So that delta H fusion of water is how much energy is exchanged in the phase change between solid and liquid, or liquid and solid, per mole of water. So the question here is, how much heat energy, remember we're looking at joules, right? Heat energy is required to melt a block of ice weighing that many kilograms, 2.50 kilograms, and we're going to assume that it has already reached its melting point. So we have already put up enough heat into this block of ice to get it to right there, to get it to its melting point. And now the question is asking, how much heat energy is required to accomplish this transition right here, to melt the solid to a liquid at that temperature. We are given the molar heat of fusion, that is the energy required to do that for every mole, and then they tell us how many kilograms of water we have. So what are we going to try to solve for? We're going to try to solve for the amount of joules, right? How much heat energy? So with this in mind, I would like for you to go ahead and try to do this problem, see if you can figure out how to set it up and solve for it. Pause the video, and when you're done, we can come back to this and I'll complete it. Okay, coming back from pausing the video, we're going to plug in some values here. This is a straightforward dimensional analysis with a conversion. Notice that we have joules and we have moles. So that delta H, you remember when we could use the delta H's as conversion factors when we did the stoichiometry of heat? Well, that's how we're going to use this here. That's how many joules of energy it requires per mole of water. So we're going to use that as a conversion factor. We're starting out with 2.50 kilograms. So it looks like what I'm going to have to do is take that number, convert it to grams first, then to convert those grams into moles of water, then use that conversion step to convert to joules at the end. So let's do it. So 2.50 moles of water. I'm sorry, 2.5 kilograms of water. And I'm going to convert first from kilograms of water to grams of water. Can you see where I'm going with this? Why do I want it in grams of water? Because I know I need to get it into moles of water to be able to do this final conversion into joules. And the only way I can get into moles of water is to get into grams first. So I'm going kilograms to grams. Then I've got grams of H2O per mole of H2O. And then I've got my one final step here, and that's using this heat of fusion, delta H of fusion of the water, as a conversion step. What goes in the denominator? It must be moles of water, so that it will cancel. And then I have to have joules of water. Oops, not of water, but just joules of energy, right? And then that will give me my answer. And you can see how all of this cancels. Kilograms of water cancels. Grams of water cancels. Moles of water cancels, and I'm left with joules. So let's plug in the values. We know that we have 1,000 grams per 1 kilogram. Per 1 mole of water, I need to add up the molar mass of water, and that's 18.02 grams per 1 mole. Where do I get these values? From that conversion factor right there. So it's 333.55 joules, 55 joules per 1 mole. So there are my numbers. The rest is calculator work. Oops, a little math error here. Let's fix that. Sorry. That answer I had forgotten to multiply by that number. So if I redo the math, then my answer is actually 46,270 joules. 46,270 joules. And before I move on, so there's my answer. I'll go ahead and circle it. Before I move on, let's make sure that answer makes sense. So this right here says that if I have 1 mole of water, it takes just over 300 joules to melt it. If I've got 2,500 grams of water, I've got way more than 1 mole of water. 1 mole of water only weighs 18.02 grams. This is over 100 times that molar amount. So I've got well over 100 moles of water here. So it's going to require at least 100 times that many joules to melt it. So if I multiply that by 100, that would be 33,000 or so. And then it should be slightly more than that. So there we go, 46,270. That makes sense. So just checking my work before I move on. And of course, this answer is not correct. All right, so that's how we calculate the heat energy required to undergo a phase transition, in this case from a solid to a liquid, to melt water. You will have to be given this value or some other value if it's some other substance other than water. Now with this in mind, if we were not melting this water but trying to freeze it, let's say it was already liquid and it was at 0 degrees Celsius, so it was at its freezing point. This would be how much energy that would have to be taken out of that liquid water in order for it to become solid. So you can see that the values, the magnitudes of these numbers are going to be the same regardless of which direction you're going, melting or freezing. But if we ask the overall change in enthalpy for this process, if we are melting, then I am adding heat, so it would be a positive value. I'm adding heat to that ice block. If, however, we are freezing it, then this would be a negative value because that water would be losing this much heat in order to solidify, in order to freeze. Okay? Once the substance's phase has completely changed to liquid, we've completely melted it, the heat energy then is absorbed to increase the temperature of the sample again. And that's what we just saw right up here. Once we have finished the phase change, then heat energy is used to increase the kinetic energy of the sample, and that increases the temperature. Once we get up to the point where we're about to vaporize the liquid to a gas, there is some amount of heat energy required to accomplish that, and that's right here. So it's this right here. This is called the heat of the delta H, the enthalpy of, or the heat of vaporization, VAP. That's the amount of heat required to make that phase change from a liquid to a gas. And that's what this is saying here. The heat energy required to break the IMFs of a liquid to form a vapor, a gas, is known as the substance's heat of vaporization. And when we're talking about heat here, we can also talk about enthalpy. And this is represented delta H for the enthalpy change or the heat change, VAP, usually a subscript VAP. Now the energy per mole to do this is different from the amount of energy per mole required to melt something. So that is to say, the heat of vaporization is a different value than the heat of fusion. So here I've given you a sample problem. The heat of vaporization of water is that many kilojoules. Ooh, look, it's a larger amount of energy per mole. So before we go on, let's just reflect on what that means. It takes more energy to get water to do a phase change from liquid to gas per mole of water than it does to convert it from a solid to a liquid. Why do you think that is? Why would it take more energy to convert a liquid to a gas than it would take to convert a solid to a liquid? Well, hopefully you're thinking about the IMFs, the intermolecular forces. When we go through a phase change, we have to break apart the IMFs, right? When you go from a solid to a liquid, we are breaking apart IMFs, but we haven't completely broken them. We've mainly weakened them enough so that one molecule of water can slide past another neighboring molecule of water. But the IMFs are still engaging each other as they do that. In contrast, when we're converting a liquid to a gas, we have to completely break the IMFs. Because we know in a gas, those gas particles are now no longer interacting with each other, right? So the IMFs are completely broken here. So here we mainly have to weaken the IMFs enough so that the particles can move past each other. But here we have to break the IMFs entirely. And that's why it takes more heat to vaporize something than it does to melt it. That's not counting the heat that it required to get it up to the temperature. We're talking now just about the heat required to achieve the phase change. And that explains why the heat of vaporization of water is so much larger, 40.65 kilojoules per mole, compared to the heat of fusion of water, which is 333.55 joules, not kilojoules per mole. All right, well, with that in mind, let's go ahead and do this problem. I've given you the delta H of vaporization of water, that many kilojoules per mole. How much heat energy is required to vaporize, that is to convert from liquid to gas, a sample of water weighing that 2.50 kilograms, the same mass as we had in the previous problem, assuming that it has already reached its boiling point. So we have the exact same sort of problem here, only now we're calculating how much heat is required to get it to boil, whereas previously we calculated how much energy was required to melt it. So with that in mind, please go ahead and try this problem. Pause the video, and when you're done, come on back and I'll work through it. All right, returning now to the video, we're going to work through this problem. It says how much heat energy is required, so I'm going to solve for joules of heat energy. That's the mass of water that I'm going to start with, 2.50 kilograms. And I'm going to use the heat of vaporization as a conversion factor between moles of water and kilojoules of water. Well, hang on just a moment. I said that I was going to figure out how much heat energy is required. Is it necessary for me to report my answer in joules, or would it be acceptable to leave it in kilojoules? Let's check the problem. No, the problem doesn't say that it has to be in joules, does it? So why don't we just leave it in kilojoules in this case? That'll save us a conversion at the end. So here I go. First conversion is to convert from kilograms of water to grams of water. Once I have it in grams of water, I can do my molar mass conversion. Grams of H2O to moles of H2O. And now that I have my moles of water, I can convert it to the kilojoules of energy. Moles of water and kilojoules of energy. And there we go. So I have my dimensional analysis set up. Everything is canceling. Grams of water, moles of water to moles of water. I'm left with kilojoules. And it didn't specify that I had to have the energy in joules, so I can leave it in kilojoules. That's acceptable. All right, plugging in values, we know that there are 1,000 grams in 1 kilogram. We know the molar mass of water, we calculated it up here, 18.02 grams per mole. Per 1 mole. And now the kilojoules per mole of water for the vaporization, that number right there, 40.65 kilojoules per mole. Okay? And the rest is calculator math. Okay, and the calculator gives me an answer here, and I have to round it to 3 sig figs because of that number right there. So my answer is going to be 5640 to 3 sig figs. Now let's compare the, oops, I forgot to do my sig figs up here correctly. When I remembered to multiply by that number, I should have considered that there are 3 sig figs right there. So this number should be rounded to 3 sig figs, right? So, goodness, let me fix that one more time. And there we go. That should be the right answer with the correct sig figs. Goodness gracious. Okay, so now we have my two answers. Let's compare these two. Notice that this number is larger than this number, but this unit of measurement is only joules compared to kilojoules. The equivalent of this in kilojoules is 46.3 kilojoules, right? So now let's compare these two amounts of energy. It took this much energy to melt the ice once it had reached its melting point. And it took this much energy to vaporize the ice once it had reached its boiling point. So you can see that there's a huge difference in these values. So again, it takes a lot more energy to cause a phase change from liquid to gas than it does to cause a phase change from solid to liquid. And that's not counting the heat required to get them up to the melting point or boiling point. That's just the heat required to go through the phase change. All right. So that's what this sample problem C is basically asking. I think you can answer this one and the following question down here. Go ahead and answer those really quickly. Pause the video and answer those. I think you should be able to answer those fairly easily now. Coming back from pausing the video, let's just answer these fairly quickly. Which requires more heat energy? Heating a 1 kilogram sample of water from room temperature to its boiling point. So we're taking liquid water and heating it up from 22.5 degrees Celsius to its boiling point, which we know is 100.0 degrees Celsius, right? Or vaporizing the water once it's already reached its boiling point. So we have two processes and we need to compare them. So we have process A. We're going to heat a sample of water from room temperature to its boiling point. How do we do that? We use the calorimetry equation, don't we? It's the calorimetry equation that's going to tell us how much heat is required to increase the temperature of the water, all right? Q equals mass times specific heat of water times the change in temperature. So the mass of water, and remember if the specific heat is 4.184 joules per gram degree Celsius, then the mass must be in grams, right? So this mass value, it's in 1.00 kilograms. So 1 kilogram is 1,000 grams. And I'm just going to put in that value for now. I know that it's only 3 sig figs, so I'll have to round my answer to 3 sig figs. But I'm just going to do that fairly quickly. The change in temperature is going to be its boiling point final minus its initial. And there we have our values, and when I'm finished, I'm going to have to round it to 3 sig figs. So that temperature change becomes a 77.5. That's what the temperature change is. And the answer that I get here has to be rounded to 3 sig figs, right? Because that mass came from that value right there. And that temperature is also in 3 sig figs. So I'm going to round my answer to 3 sig figs. And that's 324,000. And the amount of energy is in joules. If I converted it to kilojoules, I'm certainly able to do that. The problem didn't specify that I had to. But if I wanted to, I could also call that 324 kilojoules, right? So each of those is acceptable answers. Okay, so that's how much heat energy would be required to heat a 1 kilogram sample of water from room temperature to its boiling point. It takes that much energy. A lot of energy, right? Now let's calculate how much energy would be required to break the IMFs of that water once it has reached its boiling point to convert it from a liquid to a gas. And here we have our dimensional analysis, and we're going to use the heat of vaporization of water, which is given right above here. So I'm given 1.00 kilograms of water, and I'm going to convert, why not, I'll convert it to kilojoules, because the heat of vaporization is given to me up here in kilojoules. Now again, you would not be expected to memorize this. Typically, I would give you this value in the problem, but since I gave it to you right in the problem just above that, I didn't give it to you in this one. So here I go. So converting kilograms of water to grams of water. And then I want to convert from grams of water to moles of water. And then finally, moles of water to kilojoules. And we know that 1,000 grams are in a kilogram. 1 mole of water is 18.02 grams. And the conversion here is coming from the delta H of vaporization, which I would have given you in a problem, but it's right up here. It's 40.65 kilojoules per 1 mole. So let's do the calculator work. And we have to round to 3 sig figs, so my answer, 2260 kilojoules. So let's take a look at what this is telling us. This is the amount of heat energy required to heat the water up to get it from room temperature to its boiling point, and that is converted into kilojoules, 324 kilojoules. This is the amount of heat energy required to make the phase change occur once it is already at its boiling point. So you can see the phase change energy required is a whole lot more energy than just heating up the water to get it to its boiling point. Okay, so there again, just to reflect on, it takes an awful lot of energy to get a substance like water to go through that vaporization phase change. Final question here. Is the freezing of water, when we freeze water, an exothermic or endothermic process? So let's think about what is happening to the water in order for it to freeze. Is heat going into the water? Do you have to add heat to water in order to get it to freeze? No. Instead, we have to take heat out of the water so that it will freeze, solidify. Well, if heat is going out of the water, heat is being taken out of the water, then that is an exothermic process. So freezing water is an exothermic process. I've included this question because I want you to think about exothermicity versus endothermicity. Just because a substance is cold does not mean that it's endothermic. Instead, what we have to think of is heat being added to the substance, or is heat being released from or given up or going out of the substance? And that's what determines whether something is exothermic or endothermic, not whether it feels hot or cold to us.